Okay, so yeah, so we have started talking about the motivation. So basically, yeah, it's very important to be able to decide. This is why we need machine learning, and then we need real-time machine learning, real-time analytics, because things are changing. Okay, and then when things are changing, we need to adapt to the changes on this. No? So as before being in Paris, I was in Huawei in Hong Kong, and then there the national hero is Bruce Lee. He had this idea of be water, my friend. No, you should be adaptive and adapt to the things that are happening. So Samoa is basically a platform, open source, for mining big data streams. Okay, so for doing machine learning on real time, and the idea is that we have all the methods, and then also the idea is to work for industry and also for academia. Industry because it can be used in production, or for academia because we can build new methods. So there is a lot of research on how to do real-time analytics, but not in a distributed way. So now we are starting to do this in distributed way. We need also to do a lot of research to build efficient methods for this. Okay, so for giving you an example of why this is important, so this is an example at Yahoo. So we have this Yahoo News, and we wanted to detect spam. So if we have an initial model, okay, so we have all the data, we build the model, and then we don't change the model. This is the blue one. So we see that the accuracy is going down because things are changing. But if we have an online model where what we are doing is that we are updating our model, then what we see is that, this is much better because the model is able to adapt and is able to continue being accurate on the predictions. Okay, and also I think one of the reasons why this is going to be very, very popular in the next years is because the Internet of Things is coming and is going to be really, really huge. So, for example, in this prediction of EMC, we're saying that from the digital universe, from all the data that we have, the Internet of Things in 2013-14 was only 2% of this, but it's expected that in 2020 it's going to be around 10% and still growing. So this is real-time analytics is going to be really, really important in the next future. So the thing is that, we have all of this data. So this is, in fact, when we look at the definition of big data, it's not only size, and then this is why speed, velocity, it's really, really important. So you know this definition of the V's. So for real-time analytics, then specific the V of velocity is really important, and then we need to do that in a distributed environment. Okay, so the nice thing of Samoa is that it runs on the Hadoop ecosystem. So the idea is that, as you know, we cannot use MapReduce for this, because MapReduce, what is using is that it's expecting to have the data at the beginning, and then we split the data, we do the mapping, and then we do the reduce. But on real time, instances are arriving one by one, so we cannot wait to have all the data and then doing the map and reduce. So this is why in the Hadoop ecosystem there are these alternative stream engines that are maybe the most famous right now is Apache Storm. That was something that started at Twitter. Then there is also S4 that was started at Yahoo. Samza was started at LinkedIn. And nowadays, maybe the ones that are more popular are Spark Streaming and Flink. So Flink is a European project that started as Stratosphere. And Spark Streaming is a project that is now it's becoming very, very popular. I think the main difference is that Spark Streaming is a batch engine that is able to do near real-time management, but Flink is a stream engine that is able to do batch. So let me try to explain this. So the idea is that Flink works one instance by one instance, and Spark Streaming works with batches of instances. So if you use Spark Streaming, you will need to process 1 second of instances, 1,000 instances. But in Flink, you can use it one by one. So the difference is that it depends on the latency. If you need, your system can wait for 1 second to have an answer, you can use Spark Streaming. But if you need the answer on milliseconds, microseconds, then you need to use a really streaming engine like Flink or Storm. Okay, and then the tools that we have in machine learning in Samoa are, one is classification. In classification, what we want to do is we want to predict some classes. So it's going to be some labels. So we want to predict if it's positive or negative, if something is going to go up or down. Okay, so now I'm going to explain a little bit what is MOA. So MOA is a software that is only for one machine. So MOA is a software that was started at University of Waikato in New Zealand, the same as Weka. That Weka is a software for doing machine learning. And MOA contains a lot of methods for the typical machine learning methods: classification, regression, clustering, frequent pattern mining, and also outlier detection. And I think the most important thing is that it's very easy to use and very easy to extend. So let me show the difference between MOA and Weka. Let me try to show you how Weka works. So in Weka, what we have is that we have one data set. In this case, it's an electricity data set. What we want to do is we want to predict if the price of the electricity is going to go up or down. Okay, so we have all of these attributes here, and then the final class is this one. It's going to be up or down. So if we look at the data set is you know, as a table where we have these instances, we have these different attributes, and then finally the class, that is the thing that we want to predict. So in Weka is non-streaming. So what we do is that we have the data set, we want to classify, we choose which classifier we want to classify, we decide the evaluation. In that case, we're going to use 66% to learn and the rest to test. So we start, and then at the end, yeah, we get what's the model. In this case, it's a decision tree. And then at the end, what we get is a number that it's giving us the prediction, okay? So in that case, for this data set, what we get is a prediction of, we are doing right 89% of the instances. Okay, so this is what's the standard non-streaming. So what we have all the data set at the beginning, we apply our method, and then at the end we get only one number, that is the accuracy of the method. But this is in real time. Everything is changing over time. So we have also clustering. We have classification, but we have also clustering. And we have this nice interface where all the different clusters are evolving over time. So yeah, basically you see here we have the clusters, and here we see how the measures are evolving over time. That's the difference between the standard machine learning and the real time, where always we have this temporal component that things are evolving over time. And finally, we can use from the graphical interface, but we can also use it from the command line. Okay, so yeah, let me show you quickly an example of this. So yeah, this is going to be the same data set as before. We are going to try also a decision tree, and then we see when we run this. Okay, what we see here is that the accuracy, instead of being only one number, is one number for each one of the instances. So this is why accuracy is changing, and you see it's not the same for all the instances. The instances are evolving, so this is why we need our methods to be adaptive and change over time to adapt to these things. If we look at clustering, what we see is that we can select what are the two clustering methods that we want to compare. Then we can visualize this. Okay, we can start, and here we see how this clustering is evolving over time. So these are the points that we had at the beginning, and then from these points we want to get the final clusters, and we see only what are the results. And to do this on real time, we need this idea of micro clusters, that is like a subset of points that are representative of the data, and these are the ones that allow us to do this. Okay, so that's what's MOA. So now let's move to SAMOA. So the idea of SAMOA is that yeah, MOA is only working for one machine, and the idea is that at Yahoo there were needs to do that on using many machines and doing that on using the Hadoop ecosystem. So this is why we started this project. So the idea is the same. We are going to have all this data that is arriving continuously. We are not going to store it, and we need to be able to do the machine learning very, very fast and still being very, very precise. So usually you see that we are always using approximate methods, because as we are going to be very, very fast, we don't want to have the exact solution, but we prefer to be really, really, really fast. Okay, so if we look at the libraries on machine learning, the idea is that, yeah, as we have in the non-distributed way, there are the batch libraries as scikit-learn, Weka, R, and the stream, we have MOA. The idea was to have something similar in streaming for the distributed. So in the batch, Mahout used to be really popular, so the idea was to have also something similar for streaming. The idea is of Samoa was to be very, very flexible in having extensions, so we can extend it implementing new machine learning methods, new classifiers, new clustering, new frequent pattern mining methods, but also at the same time, the nice thing of Samoa is that it can run on top of all of these stream engines, on top of Storm, Samza, and Flink. And the idea is that if there is another one, as all of these, they share the same way to do things, then it's easier to add a new stream engine. So nowadays, what we have is that we have already implemented this vertical housing tree that I'm going to talk a little bit later. We have also a clustering method, in that case it's clustering, and also we have these adaptive model rules for regression. And the execution engines that we already have now are Flink, Samza, Storm, and yeah, let me show an example. So here, imagine that we have these two processors, processor 1, processor 2, and then we join them. So we have one stream from processor 1 to the join processor, and from processor 2 to the join processor. So it's very easy, the API. So what we do is that we have a topology builder. We create the first processor, source 1, we create the second one, then we create the join, and then basically we add the processors to the topology, and then we create the streams. This one, the second one, okay, and then finally we put them all together. So it's very easy to create these topologies, and then once the topology is created, the topology is executed on real time. Okay, so yeah, let me finish talking about the vertical housing tree. So this is an implementation of a decision tree in Samoa. So the properties of this is that it's going to be streaming and it's going to be distributed. So yeah, let's start with an example. So the idea of a decision tree is that it's a very easy to interpret model on machine learning. The idea is that we can have a lot of models in machine learning that are very efficient but are very difficult to understand. The decision tree is very useful because you understand what is going on and how the decisions are made. And this is why in many organizations that they deal with persons, then they prefer to use this type of models. So what is a decision tree? The idea is that we have these nodes. That is, in these nodes, what we have is an attribute, and then we have different branches. So for example, in this case, we imagine that we have instances that are giving data from if we want to have a car deal or not. So the attributes in this case could be was the road tested, mileage, age of the car, and then in that case we have this decision tree that says the first node is the road tested. If yes, we continue. We look at the second attribute, it's the mileage. If it's high, we continue, and then depending if the age is recent or old, we decide if we do the deal or not. Okay, here if we decided to go to low, in that case is yes, but here if it was not tested, the decision is no. So you see, it's very easy to interpret, and then it's very easy to see how the decisions are made. So how this is done? The idea is that we start with the first root node, and then what we look is to see if there is an attribute that is really, if we split, we are going to gain, we're going to have a gain on doing this. And then if we effectively, if all the instances were from the same class, then we don't need to split, and it's very easy. But if the instances are, we have instances from different classes, then we choose what is the best attribute, and then we do the split. Then with this one, we continue and we do the split. Here, in that case, it does not make sense to split because all the instances are from the same class. So that's, so that's more or less what's decision tree. The problem is now, to do this split, basically we have all the data in memory, and then what we do is that we need to decide to split. We look at all the data in memory, and then we decide to do the split. But in streaming, we cannot do this. The problem in streaming is that we don't have the data in memory. So how we do that? The idea then is to use what is called this HOEFFDING tree. That is now is the state of the art on decision tree for stream mining. The idea basically is that what we are going to do is, instead of using the data in memory, we are going to wait 2 new instances to arrive. Okay, so if we want to decide to split and we don't have enough information, so we cannot look at the data because we don't have it. So what we do is that we wait 2 new instances to arrive. And then using the HOEFFDING bound, this is why it's called the HOEFFDING tree, then we have statistical security that the split is well done. So this is what's the HOEFFDING tree. Okay, so now we wanted to do it in a parallel version of this. So there are several ways of do this parallelization. One is doing it by task. Okay, so what we can do is that we can divide by task, or we can divide by data. And then the data, as you see, what we have is this. We have these instances, and we have the attributes. So there are 2 ways to do this. We do this by dividing by instances. This is called horizontal parallelization, or we can do by attributes, and then we are doing it vertically. So yeah, so there was this work that was doing it horizontally, and here what you see is that, okay, we have this stream, the instances that arrive, the instances are split into different stats nodes, and then this node with the statistics, they send the histograms to a centralized model, and then this model gets the updates. So let's see an example. So imagine we have this instance. So in this instance, this is the class. The red is the class attribute that we want to predict. And these are the rest of attributes, and we want to see what's happening with the second one. Okay, the second one is the green. So in that case, this is horizontal parallelization. What we see is that for this instance, the second attribute, the green one, is going to this node. A new instance arrive. So in that case, yeah, we are distributing instances. So in that case, this goes to a different node. Okay, so the same data from the same attribute is going to different nodes at the same time. Okay, then they are aggregated, and then they go to the centralized model. So what we did is that we analyzed a standard HOEFFDING tree in MOA. So what was the time consuming, what were the time spent, and we realized that it was in the learning more than in the splitting. So this is why we went for the vertical distribution of the data. So the vertical HOEFFDING tree works in this way. So what we have is a centralized model, the stream that arrives, and then what we do is that we divide we have nodes with the statistics, but we divide them by attributes and not by instances. Then with the information of this, we ask for the information to do the splits, and then the centralized model decides if we split or not. So yeah, the same example as before. We have this instance. We are going to look at the second attribute. So here, the instance arrive, goes to the node inside the tree, and then the second attribute is sent to this node where it keeps. A new instance arrive, and it, of course, is going to happen the same. Goes to the tree, to the node on the tree, and then it is sent to the same node. So yeah, that's the difference. So here, all the attributes, the information of the attributes, are kept in the same node. Okay, so the main advantages of doing this vertical is that when we have a high dimensional data stream, then it's much easier to distribute it. And also what we find is that, yeah, in terms of efficiency, was also very, very good. Yeah, to see how it works, basically what we have is that you have the source that is arriving, the decentralized model. Then we have these nodes where the statistics of the attributes are kept. Basically, we send the information, we send what are the new statistics that arrive, and then we ask if we need to do split, and then these nodes give us back what are the split decisions. And finally, as we are evaluating, we have also an evaluator that is evaluating how well is doing our model. Okay, if we look at terms of accuracy, what we see is that we get the same accuracy that the standard HOEFFDING tree in MOA. So here is we are using a artificial generator of data following Twitter. And then what we see is that, yeah, the accuracy is basically the same, but what we have is the advantage of speed. So we can process more instances by second. So that's the main advantage of doing that distributed. So, yeah, to conclude, the idea is that I think real-time analytics is going to be very, very popular due to the Internet of Things. This is something that is coming. And yeah, we have these two open source projects, MOA from University of Waikato and then SAMOA that is distributed. They both are open source, so you can look at the code in GitHub, you can download it, you can also contribute. So it's very nice. Still, there are many open challenges. Still, it's not something that it's done and there is no something else to do. There are many things. We have things on research, but also in how to build this, how to improve scalability, how to improve velocity. So still, it's really exciting because there are so many different research to do and many things to improve. So finally, yeah, to know the team. So we have this project started at Yahoo when all of these people were at Yahoo. So yeah, the leaders of the project right now is Gianmarco, Francisci Morales, and Nicolas Curtelli with me. And then we have also Mathieu Morel, Into Murdopo, and Olivier Vander. And also, yeah, we are very happy to all the organizations that have been supporting us during all of these years. And yeah, so it's open source, so we would like very much that you like it, and if you want to contribute, you are very welcome. So thank you very much.
Thank you very much, Albert. So now if you have any questions, we have time.
Yep. Hello, thank you very much for your presentation. It's really interesting. I would like to know in which part of the pipeline do you, well, in Samoa performs the preprocessor, the cleaning data and all the stuff. How you know which of the instances held the better attributes to push up or down the accuracy of the model? Because at the end you need to know which are the instances that has the better attributes. In which part of the pipeline are you doing it?
Okay, so yeah, it's a very thank you. So it's a very yeah, important question because yeah, how we are doing machine learning in practice. So machine learning in practice are two things. One is pre-process the data and then use a machine learning model. Okay, so these are the two things. In terms of time, you see that data scientists are spending 90% of the time pre-processing data, and then at the end, 10% of the time only building the model. So if you look, for example, there's these famous Kaggle competitions where all data scientists compete. So some companies put a data set there, and then they should yeah, get the best accuracy. So usually you will see that always is data processing the one that is making the difference. So in all of these big data systems, you will see that most of the time what is done is pre-processing the data to get it into a nice way so then you can use it in the machine learning model. So what is more important is how you pre-process the data, and then yeah, then this is important to use that yeah, inside the pipeline, and then at the end, when you have this, you yeah, you use it you use your machine learning method on top of this. So in general nowadays, maybe in machine learning, there are two different visions. So one way is to use deep learning. So this is very good if your model, your data is very, very complex, okay, and then the features that you have are not enough, and then you need to build new features using this. So this is why deep learning is very good for this. The disadvantage is that you need a lot of resources, you need GPUs, you need really, and it's going to take a lot of time. The other way is that if data is simpler, then the methods that nowadays are working very well are the ones that are based on ensembles of decision trees. That could be a random forest or yeah, gradient boosted decision trees. So these are the ones that the people are using the most. So that depending on the needs, so usually data scientists is not easy in the sense that, okay, you have your data, it does not depend on the data, you use your model and it works. No. So depending on the data, you need to study a lot of the data, and then you decide how you are going to pre-process it, and then what is the best model for this data. This is why data scientist is not an easy job. So because you need to have a lot of experience working with different data sets, and then you need to spend a lot of time looking at the data set and looking and analyzing the data set to see what is the best methodology you can use. Okay, thanks.
So we have time for more questions if you want. No more questions? Yeah.
Hello, thank you for the presentation. I'd like to ask about the difference of processing data or doing machine learning in the traditional way when you have a set of data, and the way that you are implementing that is using via data streams.
Mm-hmm.
So, well, I don't know anything about machine learning, but I suppose that when you have a set of data, if you apply the algorithms, you could have an deterministic output about the result, you know, of applying this algorithm. But when you have an string data, let's say that the string at the end is going to be the same that the traditional way, for example, the question is, when you're using an string, the first results probably are not very accurate because you don't have the whole data to process it. So when it's safe to take a decision about data streams? Because, well, at the beginning probably you don't have enough data to be confident in the result.
Yeah, thanks. That's a very nice question, because that's true. Because at the beginning you start only with one instance, and you have one instance and you build a model. So how accurate can be a model with only one instance, 2 instances, 100 instances, 1,000 instances? So yeah, that's the disadvantage of data stream mining. So usually what you do is that you need a window at the beginning. You can decide it's 10,000, 100,000. You build your model there, and then you start evaluating and using it from there. So in practice, what you are doing is basically, you need some data to start, and then once you have this data, then you could continue. So an interesting thing could be try to get, if we want to be really optimal, could be, for example, use 1,000 instances, and then try to use Weka, for example, to build first model, and use this model, and then continue updating this model. That could be an option to try to get it fast. But in practice, usually the nice thing of data stream mining is that you get a lot of data arriving continuously. So then it's only at the beginning, but once the model is built, then data is going to arrive continuously, and then it's not going to be a problem. Okay, thank you.
Hi, Thank you
Hey.
for your presentation.
Thanks.
I have one question. When you mentioned about when the data model is centralized, does it mean which is in one node of the cluster? Or
Yeah, that's yeah. Thanks. That's a very I like the question. So the idea is that as I show you, there is only one model, no, and then this is centralized. What in practice, what we are looking right now is that maybe it does not make any sense, no. So maybe, and now what we are experimenting is with having several models distributed, and then how we can use this to improve our So it's that's the basic strategy to start and think. But if we want to improve the performance, if we want to do, then maybe it's a better idea to have this model replicated and then try to get the best of this. Yeah.
Okay. Thank you.
Any other question? Just to remind you, we have some delay, so we have 20 minutes delayed of the schedule. So next talk it will start at 11:30, I think. So we still have some time for more questions if you want. There.
Hi, and thanks for your presentation again.
Yeah, thank you.
I have a question about the topology builder, because when you have mentioned the topology builder, should you know your machines and you have your topology be known by you, or Samoa helps you in some way?
Yeah, so the thing is that in fact Samoa, what is a high-level API that is working on all of these stream engines. So then the problem here is that maybe, so they work, Storm, Flink, all of these, they work in a high level in the same way, but then there are a lot of details that are very, very different. So then what happens is, for example, for this, that depends on each one of the stream engines. Usually they don't grow, so you need to define topology at the beginning, and then you cannot change on that. So I think this is also something that it could be nice to do some research and see how we can do that, because this is something what happens in real time. No, in real life we have these different use cases, and then the things are not static. So also the needs that you may need is also evolving, and then also the topology could be evolving and changing over time. So this is something that I think in the future should be something very basic, no, that the system should include. I think right now still is not there, but definitely it should be something that it should be there. Yeah. So thank you.
Thank you.
So anyone else wants to make a question? Okay, so well, thank you very much. Thanks everybody. Thank you, Albert.
Thank you.